Okay, so we can start the class now. And today we have the pleasure to have here Mary Tonini. She's a scientist working at the University of Lausanne, and she's working with the modeling of geospatial phenomena, such as, for example, how forest fires propagate and how they affect different geography. So without any further ado, I will let her speak. Well, thank her for giving this very nice presentation. Please.
Thank you, Giovanni, for inviting me. And so I will talk to you today about a data science approach for wildfire risk assessment. First of all, something about me. I am an environmental spatial data scientist, and I have a strong interest in modeling for risk assessment, mainly related to wildfires and landslides. I had my PhD in Italy in agroenvironmental modeling, and then I moved in Lausanne University in 2004 as a postdoc within the group aided by Professor Michael Karneski, and I started working there in machine learning and spatiotemporal statistical analysis. And then since 2010, I was appointed a senior researcher at the Institute of Earth Surface Dynamics in Lausanne University in the Faculty of Environmental Science. I was in your place actually last Christmas last year in Kiruna in the north part. But actually, if you want to know something more about me, I prefer summertime and the sea. But in Switzerland, the environment is closer to Sweden than to Italy, and so we have more landslide than wildfires. But also wildfires are starting to become a huge problem, also in relation to climatical changes, also in the northern country. You can have a look to my scientific publication on my profile. Here is the address of my archive. And as I told you, I'm an environmental scientist, but I believe that cross-disciplinary collaboration make it possible to improve the adaptation of a method and to reach a very deeper, better understanding of all the process in my field for environmental process. So I'm not a computer scientist. I developed some skills, but the way on which I work, it's in an interdisciplinary group where we can merge different skills. My main research axis focus on the development and application of innovative approaches to enable efficient learning from complex environmental data set. And I focus on two main subjects. One is understand the spatiotemporal dynamic of Earth surface environmental process, like again wildfires or earthquake or wildfire or landslide, and also to evaluate which are the predisposing factor. About predisposing factor, I will talk you deeper later, and we can see some example later on. Method that I use, I adopt statistical models from point pattern analysis and machine learning algorithm to the case environmental data set. And application, again, mostly wildfire and landslide. And because of the lack of time, I will talk to you about wildfire that represent, in my opinion, a very complex phenomena and complex system. I don't know if you have already an idea, background about data science, maybe yes. So don't hesitate to interrupt me. I cannot see your chat, but Giovanni can advise me about that. But just in case, if you want, you can unmute you and interrupt me if you have questions. Otherwise, we make some pause later. So my research deal in the huge domain of data science, that it's still something a little bit fluid. It was defined for the first time by now in 75 as the science of dealing with the data. It means that it's something around the concept of having data, manage data, process data, apply some algorithm in order to extract information from data, to transform data from data to information and knowledge. Is a discipline that combine different domain, mainly these three domain. I like this design, this schematization of what is data science that include expertise domain, programming and acting skill that it's maybe closer to your field, and mathematical and statistical algorithm, again, to transform knowledge, data to knowledge. So we need also the expert of the phenomena, algorithm and computing and the programming. Here again, more in deep, the process of that around the data science, we have the reality. In my case, it's the geography, it's the world, it's a spatial phenomena that occurs in the world, in the earth. So we have the reality, we collect raw data. We'll see some example later. Data are processed and cleaned. The first step normally include the exploratory data analysis, something to explore the pattern of the data, the mean, the standard deviation, and just the spatial distribution, if it's normal or not, if we need to normalize the distribution or not, etc. This is exploratory analysis. And then we apply a model and algorithm. More and more, we record to algorithm from machine learning to produce data, to communicate our results, and finally to make a decision. Nowadays, we face to a gap between the generation of a big amount of data that are often heterogeneous data and our capability of understanding of them. And this makes it difficult to extract useful information and to discover pattern in data. And from this, it came data science. Collecting data, homogenize data, and understand extract information, which is the main objective of data science. In my domain, I work in data science in the field of natural hazard. First of all, what is a natural hazard? Natural hazard is a phenomenon that might have a negative effect on humans or on the environment. Are natural hazard wildfires, earthquake, landslide, tsunami, etc. And it's very important to map them, both for research goal to better understand the phenomena, but also for protecting the area, for civil protection, for example, programs aiming to diminish the human and material losses. Raw information come from multi-temporal inventories. You see here some example of raw information for wildfires, for example. This is the MODIS, our satellite. It's a satellite product that detect Barnet area and also active fires. It's a MODIS hotspot fire detection. And here are examples of inventories at a global scale of earthquake and landslide. And so this mapping just the raw data, it's very important. But then for risk assessment, it's also important to see which are the more affected area and how area can be affected in the future based also on the factors, on the variable that can influence the occurrence of these events. And I will talk about this in showing two examples. In the first part, the first example that I will give you, it's in wildfire. It's an application of wildfire risk assessment, and mainly in Portugal. I will analyze the spatial temporal pattern distribution of these events in a very long temporal data frame to see where and when these events are more concentrated in space, but also in time. And in the second part, the second example concern wildfire susceptibility assessment with a case study in Liguria region in Italy. And in this case, I applied a machine learning based approach to elaborate a susceptible map, risk map of wildfires in the area. The first, I don't know if you still have some question. Otherwise, I go on with introducing you this case study. So point pattern analysis for environmental hazard. What is our hypothesis testing? We wanted to investigate and to prove if our events that are distributed in the space are randomly distributed or are clustered. So our hypothesis testing is to verify if events distribution are expected or unexpected relatively to some statistical model, usually a random process. This is an example of spatial random distribution. In this case, I originate a random distribution of 100 events. And this is just one occurrence of one possible random distribution. You can trust me, this is a random, even if you can probably detect some empty space here, and maybe some cluster of events that means that some events are closer in space in some spot here, for example, or here. Nevertheless, this is a random distribution. It means that there is an hazard behind, and events are not closer than just that can be by chance. How we can, so first of all, why this is important? Because if they are randomly distributed, we cannot discover really which can be, for example, for wildfires, the predisposing factors. But normally, hazard events are not randomly distributed. Normally, they are clustered and discover where are the overdensity. It's very important to detect which are the factors that can predispose the area to be susceptible to these events. How we can detect if this distribution is random or not? We can use a quadratic analysis. So most of the cluster analysis, the cluster indicator, are based on the quadratic analysis. Here are the three examples, the basic example of three possible distribution: the random distribution, the dispersed distribution, and the clustered distribution. We have a dispersed, or it can be also regular distribution, where you have the events regular distributed over a regular grid. And this is quite improbable in the nature, in the reality. We can have this, for example, for some vegetable or animal distribution, species distribution, where you have a high competition. In vegetable, for example, if you have a lot of competitors, they tend to be far away one from another compared to the random distribution. What is much more common is to have a cluster distribution, where effectively you have several huge empty space, and on the other hand, you have events that are really closer to each other than expected for a random distribution. How we can detect? We can use quadratic analysis, and it's something very easy. You just overlap a quadratic grid over your data, and you count, so you have n square quadratic square range, and you count the number of events over that fall inside each quadrant. So you can compute the mean, the number of events inside each grid over the number of n, that it's the total number of these quadrats. And you can compute the variance. And what is important is this value that represents the variance to the mean ratio. We can determine, you can easily compute the value of this variance to the mean ratio. And for a random distribution, this value is closer to 1. For a dispersed distribution, is less than 1, and for a clustered distribution, it's above 1. It's a positive. It's a value higher than 1. So this is a very easy way to evaluate if a distribution is clustered or not. And then you can, for example, use in a Monte Carlo testing, so you can compute 1,000 of random distribution and to see if this is really statistically clustered or not. But this is just to give you an idea of how mathematically we can compute if a distribution is clustered or dispersed or random. We have a different indicator, mainly global indicator, as the Moran index, Allen factor, the Ripley K function of fractal dimension, that are very, the basic assumption is this quadratic analysis, and this allows to determine if a distribution is random or clustered. And then you have also local methods to really detect where these clusters are localized. You can look at some publication of mine where I applied the scan statistics to localize a cluster in space or in time, but we focus I will focus my presentation of today on global indicator. Are easier to, not easier, you say you can broadly apply a global indicator, while for local analysis, you need a reference population. So if you have I've not a lot of time, but if you have a question, I can give you more information about local indicator as well. So application to wildfire. It's in fire management, it's very important to try to predict where and when fires are more likely to occur. And how we can do, looking at the past events. So we make prediction normally looking at the past, at the history. And this, it's a key information to understand the predisposing or triggering factors of ignition. Here you have still another example. This is the FIRMS. It's a Fire Information for Resource Management System. It's a platform from which you can download inventories of wildfires at a global scale, identified as a Barnet area or just as a pixel, so ignition point of the fires. You can already verify that these events are clustered because, of course, you have forest fires wildfires where you have forest, and so here in the desert you don't have fires. You have in some desertic area, of course, you don't. So fires are naturally clusterized where you have the forest. Nevertheless, these also in the forest are not randomly distributed inside the forest, but are clusterized in the forest where you have more prone vegetation, or in some period where the season is more prone to fires, or depending on the slope. But since 95% of fires in Mediterranean area, so what they are called and defined as anthropogenic fires, are of anthropogenic origin, it's 95%. We can, in literature, we can verify that they are really close to anthropogenic infrastructure. So they are distributed in cluster and not randomly. So the example, the case study is in Portugal, that it's a country very prone to fires in southern Europe. Something about the geography and the special distribution of fires in Portugal. So the southern part of the Portugal, that it's south of Tagus River, that it's around here. It's more agricultural area, and in the northern part you have a much more forest area. And so most of the fires develops in the northern part than in the southern part. Here it's some global statistics about analyzed events. They span 23 years period from 90 to 2013. So the data are provided by the Institute of Conservation of Nature and Fires, and consist in observed fire scars, so Barnet area above 5 hectares. And here you can see something quite interesting, that not every time so you have, so here is the distribution by years, so you can see the distribution of the number of the events, but sometimes in some years, for example, in 2003 and in 2005, you had a lot of several fires in terms of number of events, but not in terms of Barnet areas. These are not every time, they don't follow every time the same distributions. And normally you tend to have a lot of small fires and less big fires. The method that, so first of all, what is the main objective of this analysis is from this distribution, so you have a dot and point, the main goal is to elaborate a smoothed map of density distribution of fires, but a three-dimensional map. We want to see how they are distributed in space, but also in time. So the third dimension is the time. Because here you can just verify that are more densely distributed in the northern part, but we cannot see where, in which years, for example, if they follow a temporal distribution too. So the method that we applied, it's a global cluster indicator, the replay K function. It's a statistical exploratory analysis which allow to detect if a point process is or not randomly distributed. The basic function was developed for spatial distribution. And the K is computed as the number of future events occurring within a distance R from an arbitrary event. So you have events distributed in space. For increasing distances, it counts the number of events inside. So the expected number of events compared with the lambda, that is the special intensities, the number of events for the unit area. And what happened is that for a random distribution, this value of the K is equal to the area of the circle, so P R square. If events are clustered, the K have a value that is higher than the area of the circle. And for a dispersed distribution, it's lower. So we just computed this K value, knowing the number of events by area and increasing this radius. And for increasing the value of this distance, we can evaluate at which distance value our distribution is eventually clustered, dispersed, or randomly distributed. An improvement of the K function is the spatiotemporal K function is computed in the same way, but it accounts for the number of events at a certain distance in space and in time. So events are computed over a cylinder where the height of the cylinder represents the time years, for example, number of events by months, by week, or by years. Then what it was the novelty of my approach, it was to use this distance value on which we can estimate the distance for which our events are more clustered, and I use this value as a bandwidth for a kernel. What is a kernel? A kernel is a non-parametric descriptors tools that is widely applied in GIS science, in spatial data science, to elaborate a smoothed density surface. So it allows weighting the contribution of each event based on their relative distance. And this distance, it's evaluated over a Gaussian distribution. So there are several parameters. I go not too in deep that we need to fix. So for example, which kernel and which Gaussian we are going to use. But what very important parameter is the bandwidth of this Gaussian. So at which distance you are going to evaluate your kernel. Again, it exists also a spatiotemporal module for the kernel density estimator. But what it's important, it's to evaluate this bandwidth, because if you use a bandwidth too narrow, too short, you have an over-smoothed map. And if you use a value too large, you have a under-smoothed map. And so this bandwidth is very important, and we use again the value that we can compute using the K function. Here it's just to resume and make for you more clear what I explained to you up to now. So this is the general scheme of this investigation, this project. We have the input data set that are forest fires inventoried over several years. Here you have, for example, 3 years, but in reality, we investigated 43 years, for 19 to 2013. So we, for each year, you have, so not for each year, also if you consider the entire spatiotemporal data set, you have these events. You can consider these as the ignition points of each fires, or if you want, the centroid of each Barnet area. So you can interpret each fires as a point. Is the starting point of the fires, if you want. And so these are distributed in a 3D space, so in space and in time. So I applied the K function, in this case, the spatiotemporal K function, to detect and to determine at which distance value these events are clusterized, form cluster, are more close in space and in time. I use this distance value that I obtain from the K function as a bandwidth for my kernel. And this allowed me to elaborate this smoothed 3D kernel map of wildfire distribution in Portugal in space and in time. Why this is important? Because it allows me to detect hotspot in space, but also to detect in which period along my 33 years of investigation I had more fires. Step by step, I started collecting the raw data that consists in the Barnet area of wildfires. And so here you see just for 5 years, but I had for more than 20. And so the question is how we can discover pattern. First of all, we simplified this data, considering the centroid of the data. And so the XY coordinate for each Barnet area. And of course, for each event, we have also some attributes consisting in the time and in the area. So the year of occurrence and the area. So the first, to simplify, the first step, it was to grouping the data by Barnet area intervals, because normally the large, medium, and small fires have different dynamics, and so we grouped it in these three groups. So they do this. Do they display a similar pattern distribution? We compute the 3D in this case. It's the D plot, the 3D plot of the kernel. Of the K function, the spatiotemporal K function. It's maybe not so clear. I don't know if it's clear or not for you, but so here it's the increasing distances in space and increasing distances in time. These are years. Here for the small fires, you can see that they display. So first of all, I have to say, okay, I have to introduce the spatiotemporal K function. Yeah, because I introduced to you before just the spatial. Sorry, I go back just here. This is the spatiotemporal K function, how it's computed. And finally, we can assume this is the spatiotemporal K, that you can compute the difference between the spatiotemporal K and the product of the simple spatial and the simple temporal K function. If this difference is equal to 0, you have a random distribution. That means if the spatiotemporal K is equal to the product of the simple spatial and the simple temporal K function, the two variables, space and time, does not interact between them, are not correlated. And so you have a not correlation between space and time. So what we want to determine if space and time interact in creating spatiotemporal clusters of wildfires events. So we plot this is the D plot. It's the plot of the spatiotemporal K function. When it assumes values close to 0, it means that this difference is equal to 0. You have no interaction, no spatiotemporal cluster. For positive values, you have an interaction. But what we are looking for are the peak of these values. Here, for example, we'll see later precisely these values. You have a peak in the temporal dimension around 2 years for small fires. But for large fires, you have this peak of a clustering around 6-8 years. And this is quite interesting because normally it can suggest that the return time following a large fires, it's longer than for small fires. So if you have a large fires in an area, you don't expect having another large fires 1 or 2 years later, but you have to wait, fortunately, several years. And this it's given for the regeneration time needed to the vegetation, mainly. But also, it's clear that the distribution of small and large fire is different. So also another thing that I've done, it was to analyze separately the northern and southern part of the country, because as I showed you before, we have much more fires in the northern parts of Portugal than in the southern part. And what it was important, it was to determine metrics from these values, from this K function to evaluate the kernel bandwidth that allows us to elaborate these maps, these 3D maps, density maps. So finally, by the deep plot and the deeper investigation on the tabular values, giving us the value at which data are clustered, we determine this value for small, medium, and large fires, and for the north and the southern region. So in space, small fires are clustered up to 10 kilometers and in a range of 3 years. For medium fires, it's 5 years, and for large fires, it's more than 7 years. And these are the metrics in the northern and southern region. So in the southern, events are far apart one to the other, and cluster are at 20 kilometers, but closer in for northern. You have a smaller cluster in the northern part. And so finally, we used this value as for our bandwidth, to evaluate the bandwidth of our kernel. And finally, we could elaborate these density maps yearly for the northern and the southern part of the country. But what is also very nice, it's the 3D plot of this kernel. It's exactly the same yearly density maps that you see in the previous slide, but in 3D. Which are the main results is that the southern half of the country counts a lower density surface of fires than in the northern region. Also, we determined that in the central period from 98 to 2006, medium height densities are spatially homogeneous distributed with higher densities in the period from 2000 to 2004. And lower densities are registered in the years with a very low number of events. So in the first part of the first years of our investigation, but also in other periods. So we can detect in which year we have lower densities. Of course, you can see these maybe even better looking at the yearly distribution, but it's also nice to show to the decision makers this 3D map. And also, finally, we could verify that in the southern part of the area, it's most difficult to define a clear pattern, a clear trend in the pattern distribution of these densities of wildfires. In conclusion, hazardous events, in this case we saw for wildfires, but the same analysis can be performed in the case of other hazards. And this can be associated to a stochastic point process where events are analyzed as a set of geographical coordinates corresponding, in the case of fires, to the ignition points or to the centroid of each Barnet area, or for landslide, you can consider the centroid of the landslides, or you can consider the detachment points from which the landslide collapse and originates. the spatiotemporal pattern of a stochastic point process, including the cluster analysis, is very important to discover predisposing factors and for prevention and forecasting purpose. So in this presentation, I focus just on exploratory analysis, just to highlight cluster, and I didn't go in deep in discovering the predisposing factors. But in other case study, for example, we discover for landslides in Switzerland that the main clusters occurred where we had very, very strong and extreme events in terms of rainfall events that activates following landslides. But these are more complex and demanding analysis, let's say. But it gives already an idea, just looking at the distribution, it gives an idea of which can be the predisposing factors in terms for fires of vegetation, season, meteorological condition, etc. And so not only the spatial, but the spatiotemporal analysis, in my opinion, it's very, very important, very crucial in hazard and risk management. So this it's for me my conclusion for the first part of this presentation. And before to start with the second part that focus on the application of machine learning for susceptibility mapping, if you have question for this first part, you can ask me now.
Well, thank you very much for the presentation. That was very interesting. And yeah, if you have questions, please you can unmute yourself or write in the chat.
I can just add that the analysis were performed under the R environment. Normally I use R, my colleagues use Python, and normally in geoscience, the two most used computing environment are Python and R. For me, it's more R because I come from JS discipline, and so in a GIS and JS for mapping, etc. Normally, you are more R, but so nevertheless, all these computation and this analysis you can perform both with R and with Python. And from my side, I don't know if you already analyze spatial data, but for the spatial part, I use a GIS software, and here we use ArcGIS, and I use also QGIS, but most of the analysis you can be performed directly in the computational environment in R or in Python.
Can I ask a question, please?
Yeah.
So I was wondering, you said that you found it really important with cross-disciplinary science, and how is environmental science done without data science?
This is a nice question. We just we are starting. Let's say we are starting because in my faculty, for example, we have a 3 discipline in geology, environmental science, more focus in hydro and geoscience, and geographer. And up to now, we stay. Each one stay in his topic. So we have a specialist in landslides, specialist in hydrology, specialist in urban planning, etc. But we are more open also because we need more computational skills. Because we faced a lot of data, and geographer, and also, so we are not so good in computation. So we need skills from computer science, from mathematics, from physics, from algorithm, and but we need also knowledge. So we needed to collaborate. So what I wanted to just to say you is that it's just a matter of this week we open a new position for a professional position in my institute for environmental data science. It's the first time. The position before, it was geomatics, it was JS. Now it's environmental data science. And if you look at it on the profile, we were looking for someone, we selected four, we shortlisted four that have the audition next week and in 2 weeks. And if you look at that, the profile, we were looking for like a Superman or Superwoman, for someone that knows programming, mathematics, algorithms, and JS, a lot of things. So what I suggest is to know a little bit of everything and to collaborate with other scientists.
Thank you.
You're welcome.
So is there any other question? I have a curiosity. Why do they have more fires in the north of Portugal than in the south?
Because
I would have really expected the opposite.
No, because so in the northern part you have much more forest area, and also you have much more urban area. And since I think in Portugal, even 98% of the fires are of anthropogenic origin, it doesn't mean only voluntary fires, but it can also be involuntary or from some practices and also in the forestry management. But so it happened that this kind of fires happen closer to urban areas. So in the northern part, you have much more forestry and urban area. In the southern, you have agricultural area, and you can use fires also in agricultural practice. But I think that in Portugal, it's not more the case, or you can just burn agricultural residual in some period, so you can control and so avoid that they can originate wildfires.
Okay. Okay.
Can I ask a question?
Yeah.
Yes. So if you plan too close to such models where you are looking at historic data and so on, is there some risk that you miss like freak accidents, so that you like very large events which you didn't plan for because you only looked at what has happened before? And do you manage this extra risk in some way?
If you look, sorry, at the historic data.
Yes. So
historic data. It was
yes,
the question.
exactly.
Okay.
So if you plan according to what has happened before, you risk. So it's a very general question, not just for wildfires, but for prediction in general. Yeah.
You're right, and I will show you a very nice example in the next presentation. You're correct. So when we try to predict, the only thing that we can do is to look at the previous behavior, to historical data. But when we predict, we assume that things will go in the same direction, and sometimes it's not the case. And so it's something that we have to take into account. But if you will see, because in the end of the next presentation, I exactly explain what it can happen, and I will give an answer to your question.
Very nice, thank you.
Okay, is there any other question? Okay, well, so thank you for this first presentation, and I would suggest to have maybe 10 minutes break, and we have the other presentation at 11, if it's okay for you.
Yeah, okay, fine. Okay, perfect.
Thank you.
See you later.
See you in 10 minutes.
Okay. Giovanni, you can see the presentation?
Yes.
Okay, fine. Okay, still. Okay, thank you. Okay.
Let's restart.
Fine. So in this second part, I will talk to you about a machine learning based approach for wildfire susceptibility assessment. First of all, a brief introduction and definition of a susceptibility map. A susceptibility map is something a little bit different than a risk map, since in a susceptibility, the susceptibility map indicates the area with a potential to experience a particular hazard in the future based on the intrinsic local properties of the site. Again, under the basic assumption that the past is the key to the future. We considering the susceptibility, we don't consider the possible infrastructure or human losses or the elements that can be on the soil and damaged on the people that can that because of these hazardous events. You just consider the property of the soil, and if in that area you can, if that area can experience an hazard in the future, regardless of the person or infrastructure that can be affected, because these last are taken into consideration in the risk map, that it's something a little bit different. This is just to give you a brief, just an idea. So we consider just the element. If in this case, we are looking at wildfires, so we are trying to classify the area based on their propensity of experience fires in the future. And why you can evaluate this propensity looking on the past. Which element we consider to assess the susceptibility of an area? The events, the past events that are stored in these spatiotemporal inventories, so are the occurrence of wildfires in the area, and the predisposing or triggering factors. For example, the vegetation cover, the land use, the altitude, the slope, etc. That are all the ensemble of variables that can affect, that can influence the occurrence of wildfires. We use a machine learning based approach. So a brief introduction on machine learning. Machine learning includes algorithms capable of learning from and make a prediction on data, modeling the hidden relationship between a set of input and output variables. What does this mean? Machine learning, it's not one algorithm, but several different algorithms that from a computational and mathematical point of view can be very different between them, are defined as part of machine learning. What these algorithms have in common is the fact that the algorithm itself can learn the relationship between the data. Which are the data? Are the input variable. So all, for example, for the forest fires, you have again this vegetation, dam, altitude, etc., and the observation. If you had not a wildfires in the past, so you have these containers with all the data. A good practice in machine learning is to split your data set into three parts: the training, the testing, and you have also the validation data set. So you train your model on the training data set that normally correspond to the 70–80% of the entire data set. And you keep 20%, to simplify, you consider just the training and testing. We see later for validation. And then you create your model just over the 80% of your data. You keep out 20%, 30% of your data. Then you use the machine learning algorithm that you prefer: neural network, random forest, deep learning. You choose the best one based on your project and your data. And then you have a model. And you can, once you have your model, you can make a prediction on the 20-30% of the data that you didn't use in your model. And you can see if you made or not a good prediction. If you make a good prediction, if for wildfires, for example, your model can predict correctly fires and not burned area, it means that your model is robust enough to make prediction on new data. Otherwise, you have to optimize again your model. So this is the general scheme of a machine learning based approach. But we'll see deeper later with the algorithm that I use, that it's random forest. The study area, we move now in Italy, in this region, that it's a Liguria region, in the northern part of Italy. It's a very small region, but very complex in terms of vegetation cover, in terms of altitude. And so it's quite interesting. This it's just a summary statistics of the fires. It's better said, it's the temporal distribution of the fires, again, in terms of number of wildfires and the burned area. And in this case, we divided the data set according to the seasonality, because in winter and in summer, so we consider winter from September to March, and summer from April to August, or August to September. So we divided it just 6 and 6 months, these two seasons. And we expert says that wildfires in Liguria in summer and winter have two different behavior in terms of distribution, number, etc. And so we analyze the two data sets separately. So we used a machine learning based algorithm that it's random forest. So just in order to not make confusion, discussing with Giovanni, he told me that he introduced to you the concept of random forest, but it's another random forest. It's a random forest, it's a cellular automata based approach. In this case, it's a machine learning algorithm. It's something different. As concern random forest in the machine learning, as a machine learning algorithm, random forest is an ensemble algorithm based on decision tree. Why ensemble? Because it creates thousands of different decision tree, and it computes the average of its output of each result. Here are the input data set that feed your algorithm, and that consist in the burned area, that it's from a mathematical point of view, the dependent variable, and predisposing factor that from a mathematical point of view are the independent variable. So we want to predict the burned area based on predisposing factor, and based on the distribution and behavior of this burned area in the past. So we'll see later how what happened here inside, but just from input to the output is a predictive value expressed as the probability for each pixel of burning under the assumption of a set of a predisposing factor. So just let me say, when I say pixel, I don't know if it's clear for each one of you. I work with the geographical layers and with the geographical map, with the raster map. Raster, it's like an image. And so I work at the pixel level. The pixel, it's just the basic unit of each images. So for each pixel, I have a value for all the independent and dependent variable, and my output, it's a value from a continuous value from 0 to 1, representing the probability for this pixel to burn in the future. The predisposing factor, so I move here because otherwise, sorry, I think you don't see it. Okay, these are the predisposing, I don't know how to move this. Okay, these are the predisposing factor, these independent variables that I consider in the model. So it's the DEM, it's the digital elevation model. It represents the values of altitude for each pixel, the slope, that is a derivative of the DEM, the north and the east direction, again a derivative of the DEM, the distance to a road and the distance to a building. And these two factors are, as I told you before, very important in predicting anthropogenic wildfires. Protected area, if the pixel is inside or outside of a protected area. Vegetation type. I stop here. Just I attract your attention on the type of these factors. We can have numerical values, continuous values, like the DEM. You have its pixel as a continuous values from 0 in this case to 2018 and something. Slope, it's again a numerical values, but in terms of degree. The north and the east are computed from 0 to 1, so are numerical continuous values. The distance to a source are computed as the Euclidean distance to the closest source, so road or building, in meters, so as a numerical variables. Protected area are binary variables because you can be inside 1 or outside the protected area, 0. Vegetation type, it's a categorical variable. So you have the type of vegetation. It can be shrub vegetation, pine, or forest, the type, really design the type of vegetation in terms of a string, a character. So it's a categorical variables. And I like random forest because it can manage directly categorical variable, avoiding the needs implicit in other machine learning algorithm of transforming categorical into numerical. So it can directly, and this is something that can manage only the R implemented in R. We tried with Python, and this function is not implemented. So you need to transform. In this case, we can just give the categorical values. So we run two models, one considering this first set of variables, and the second one much more complicated, where we considered also the neighboring vegetation. So for each pixel, we consider the type, the percentage of vegetation around each pixel. So in the first model, we had just 10 variable. In the second model, we had to we had much more variable because we have to add all these percentages. So we had something like 15 variables. So computationally, it was very, very heavy. And so the idea is to compare the two models to see which one predict the best. It's the best in terms of a prediction, but considering also the computational timing, so the cost. So this is an example. It's not Liguria because I didn't develop this model, this design, I mean, this slide, if you want, for Liguria, but I had an example. This is a Canton Vaud, these are landslide, but it's just, since you are not a geographer, so I suppose that you are not really very close to this kind of data, of geographical data. It's just to give you the idea of how we pre-process the data to transform geographical data into a matrix, to feed a computational algorithm, to feed R or Python, our algorithm. So we have, for example, imagine that these are the Barnet area, and these are unbarned. So all the red polygon are the Barnet area, inventoried over 20 years of, 30, I think 30 years of data. So we split our data set, our observation, into training and testing data set. So we consider the 80% of the polygons of the Barnet area to feed, to run our model, and we keep out the 20% or 30% of the Barnet area to assess the performance of our model, so what we call the testing data set. We work in a raster mode, so we have to transform this polygon in raster. We just overlap a regular grid with the same resolution of our DEM, of our digital elevation model. And so for each pixel, we just extract the information about the altitude, the slope, all the variables that I mentioned you before, the distance to road, to urban area, to the type of the vegetation, protecting the area, etc. And so we have these very complex and huge metrics. And here we have our independent variables. So these are, again, the value for each pixel. Consider, for example, this pixel. Here we don't have a fires, so our dependent variable, that it's the Barnet area, assume the value 0. It's a binary variable. And so here the altitude, it's, for example, 81.2, the slope it's 9 degrees, the distance to road 30 meters, distance to house it's 57 meters, and the type of vegetation, it's a brush, and we are not in a protected area. We move now to another pixel here. Here the fire assume the value 1. So we have a fires, and so we extracted the values of the altitude, the slope, distance to road, etc., etc. And so finally we have our matrix. So how random forest works? The algorithm generates n. So we see, as I told you before, it's an ensemble model. So it generates 100 of trees. And this is just how each tree works. So the algorithm generates n tree subset of the training data set. So we consider only the training data set, and it split directly the training data set into training, and the validation data set. That in the case of random forest, it's called out of back. So it automatically count only 2/3 of the observation, and it keep out 1/3, about 1/3 of the observation extracted randomly by bootstrapping, that it's random sampling with replacement. It can go inside to the following run. And so 1/3 of the observation of the pixel, if you want, are kept outside for validation purpose. And this is called out of back. So it generated this decision tree, and at each split of the tree, it computes a Gini index. So it's a value, the Gini index, which allows to assess which variable is most important in determining if the pixel burn or not. In this case, the most important variable at the first split, it's, for example, the vegetation. And you consider that if the vegetation it's 37, it means shrub vegetation. So most of the pixels are burning. Otherwise, for all the other kind of vegetation, they are not. But if they are burning, if they are this type of vegetation, not, in reality, not all of them are burning. If the slope is higher than a certain value, again determined by the Gini index, they burn, otherwise not. And so it's split yes or not for each variable determined by the Gini index. And so the tree grows, and it stops when each node contains less than a fixed number of points, example 10%. It can grow even, you can even decide to not stop your trees, to let it grow up to the end, but it takes a lot of time for computational analysis, so it's up to you. So at the end, what happens? It happens that each pixel, it's for each tree, detected as burning or not burning. But this is only one tree. So the user has to determine and fix the optimal number of trees, and not only this, it's one parameter of the random forest, that it's n3. The second parameter is m_try. M_try is because not all the predisposing variables are selected for each trees, but only a subset of, if you have 10 variables, you select only, for example, 3 or 4. But since you create 1,000 of trees, you assure that each variable is selected. And this it's done to avoiding that the most important variable is selected every time, and so it will be overestimated. So to be sure that you consider all the variable, you consider just a subsample of them for each tree. And these two parameters have to be determined by the user. You can do this automatically. Otherwise, you can make the prediction over your out of bag. And when the error evaluated over this out of bag, this validation data set, when it's very, very low, you know that you have the optimal number of tree and of m_try. So you can assess these parameters thanks to the validation data set. This is a general way to do in machine learning, to split the data set in training testing, but also validation. And the validation, it's used internally by your model to optimize the parameter of your model. Nevertheless, this validation data set, it's a part of your model. It's not something that your model never seen, because you do several simulation, and so you use the validation data set, for example, not for this tree, but for the next one. So I know that this is quite maybe some complex if you have absolutely any idea about machine learning or this model, but of course you can go more in deep, and I provide a better explanation of all these in my paper, but you can see, of course, also on other sources. So in our case, we have a binary classification, because our pixel can burn, it's 1, or it's not burning, it's 0. It can assume only 2 values, so it's a binary. And also our output, you see here, it's a binary output. You can, it can be 0 or it can be 1. But what we want, it's a continuous value from 0 to 1, from low value, low probability of burning, to increasing medium probability to very high probability of burning. So one way that we adopted to transform the binary output in a probabilistic output, it was for each pixel to count how many times each pixel was classified as 1 over the total number of trees used on a random forest. For example, if you run 1,000 of trees and one pixel, it was classified 70 times as burning and 30 as unburning, this pixel has a 70% of probability of burning. So you just normalize over the total number of trees. And so you can pass from the binary to probabilistic output. And the second comment, it's about this 0 and 1. Of course, you have much more 1 than 0, because you have the contrary, you have much more 0 than 1, because normally you have much more area that is empty, that is not affected by your hazard, by your fires, than the area that is affected by your fires, likely. So normally it's the case. Sometimes you can have also area that burns much more, but normally you have much more 0 than 1. And you have to balance these two values. Otherwise, your model are going to overestimate the 0 values. And so in this case, I simply selected the same number of 0 randomly as 1. There are several methods to optimize this balancement of the classes balance. But in this case, I simply generate randomly the same number of 0 that is absence from fires, then 1 that is presence from fires, selected of course over the unburning areas. Our model, it's a little bit more complicated. I mean, I elaborated this model from a very practical point of view. My model has to provide to the decision makers, to the civil protection, for example, an instrument, a tools, a real tools to evaluate the susceptibility of the area of burning. It's not just for, so that it's anyway a very noble, a very good thing, but it was not just done with the final goal objective of publishing a paper, but it was really done as a very effective instrument. So I wanted to be sure that my model was really robust, and so I preferred to use an additional validation data set. I was not obliged because internally the random forest used this out of bag, but I wanted to also be sure that I could generalize my model in space. So generally speaking, again, you have the training data set that needed to train the model used to get the prediction in new data. So it's the data set that you use in your machine learning algorithm. Then you have the testing data set that contains the data that has never been used in the training step and helps with the final model evaluation. So you can predict your model on the testing data set and evaluate the error. So if you predicted correctly or not your events, your hazard. And then you have a third data set that is the validation data set. In the case of random forest, it can be considered out of bag, but normally it's a third part of your data set. It's a subset of your training data set, if you want, that provides an unbiased and evaluation of the model fitness. In this case, how I selected the validation data set. So it's a sub-ensemble of this training. So I have my area, and I use the K-cross spatial method. So I divided my area into different sub-area of equal sites that are called folds. In this case, each folds are the square that has the same color, but they are dispersed in the area. Why? Because I wanted to avoid what we call spatial autocorrelation. I mean, if I validate my model over the data that are taken very close to the data that I used to create my model, the probability that they assume the same value, it's very high. So as results, my model perform perfectly, but I used a validation data set that's very similar to the training data set. And so maybe in the future, my model, it cannot perform very well, or especially in this case, cannot perform very well in other area far apart from the training events. Okay, so I just selected the validation far away from the training events selected to be sure that if my model perform well in the validation, that it's very far spatially from the training, it can perform well, very well. It's everywhere, and it's a very good model in a spatial, from a spatial point of view. And so I create 5 and 9 fold, and so these are 2 models. And I compare the 2 models, which one is the best. The testing data set, so this is for the validation and the training, and now the testing data set. The testing data set was selected considering temporally the Barnet area. So my Barnet area spanned 30 years from 97 to 2017. And I used the first 16 years so the Barnet area from 97 to 2011 for the training, as a training data set. And I used the Barnet area inventory from in the last 6 years for the testing data set. So what does it mean? If my model that was created using the data up to 2011 predict well the events that will happen in the future, so from 2012 to 2017, it means that it can give a good prediction in the future. So I can be confident that if I use the data or the data set from 2017, I can have a model that can predict well in the next 5 or 10 years, okay? How this was done, I have my probabilistic output. In this case, I have a continuous value from 0 to 1. But in terms of decision makers, and just to transfer this information, to communicate this information to decision makers, it sounds better for them to think in terms of a percentile. So what they can easily assess is the 25% of the area that has the lowest probability of burning. This is the first 25%, that's the first quartile. Then the 50% of the area that has the lower or the highest probability of burning. If you look on the other side, the 95% percentile are the red area, correspond to the 5% of the area that have the highest probability of burning. So I want to validate, to see if my model can perform, can give good prediction in the future. I look if these are the Barnet area, for example, detected in the testing data set, so 2012, 2017, not used to create my model. And if I have a good model, I'm expecting that this area fall in red pixel. So in the area of my map that are predicted with a very high probability of burning. So if I have a good model, I have this as results: the testing burning area falling in the red percentile, high percentile classes. But we look the results. Finally, I have 4 results. One result, it's the comparison of the standard model, where I used just the first set of the variable, with the neighboring vegetation model, where I used also the percentage of the type of vegetation around each pixel. That it's by itself a very important variable, but it produced a model that it's very complex, because I have to add to my first 10 variables 37 additional variables. So my model, for sure, it's very heavy. It's very important to use the simplest model. If you have 2 models, one very simple and one very complicated, but the simple one give the same prediction as the same predictability accuracy, use the simplest one. So if I can describe my world with a simple model that describe perfectly my world, I use the simplest one. It's because of this that I compared the 2, but if the simplest one perform as the complex one, I prefer to use the simplest one. Then I compared also the model where I used 5 or 9 special folder for the special cross-validation. And another result is, of course, the susceptibility map, and also the evaluation of the predisposing factors to the model. These are the results of in terms of model validation. I compare the performances of the model using 1 fold cross-validation, 5 and 9. 1, it corresponds just to use 80% of the data randomly. And this if I use the special cross-validation. These are the percentage of the testing Barnet area. So the Barnet area, the area that burned in the last 6 years of my inventories, which percentage fall inside the predicted Barnet area of the last quartile. So 75%, it represents the 25% of the area with the highest probability of burning. Of course, I'm expecting that the testing burned area fall inside at least this highest 25%. And in fact, this is the case. And the model that have this that give the highest values in this last quartile is, for me, the best model. As you can see here, using the increasing the number of folders, the predictability rise, but using 5 or 9 folder, it doesn't increase your performance. So you prefer to use the simplest model with the 5 folder. Nevertheless, considering the neighboring vegetation, even if you have a more complex model because you add much more variables, you have better prediction. So finally, we consider, at least in the winter season, the 5 cross-validation model using also the neighboring vegetation information as the best model. Another thing that you can notice is that in summer, the model perform not so well as not so good performances as in winter. Performances in summer are a little bit lower. Here you can predict 87% of the burning area in the last percentile, while the same model in summer predicted about the 75% of the area. And we will discuss about this later. Now, not later. So our question was why we had why we lose in performances, especially in summer. So instead of considering all the burned area altogether, we split it by year. So we considered in this case, again, the last percentile of the testing burned area over our map, and for the winter and the summer season. And we saw that in winter season, burned area detected on each testing years attest for a good performance of the model, in some case with very high value, 90% of the area, but anyway higher than 80% so for each year. In summer, what happened? It happened that each year gives quite good performances, a little bit less in 2012, but very, very, very bad performance in 2017. In summer 2017, less than 50% of our burning area was predicted by the model. So this it's something that was asked before by your colleague. If I use historical data, I'm sure that I can predict in the future. In this case, not so sure. So it's not the case. And so we will see what happened in summer 2007 and why our model fails. Final results, it's the susceptibility map in the winter season and the susceptibility map in summer season. And as I told you before, you see that the behavior is quite different in the two seasons, more in the coastal area in the summer, and more fires develop more in the interior area in the winter. And here I overlapped the testing burned area to the susceptibility map. And here it's a zoom. And indeed, you can see that some of the burned area doesn't fit exactly, doesn't match with the red high probability predicted area. As in this case. In this case, it's quite interesting because maybe our model could correctly predict the ignition, but not the spread of our fires. Why machine learning in general can fail, and in particular, why our model fails to predict burned area in summer 2017. In our opinion, we investigate the reason why, and in our opinion, it was because summer 2017, it was a quite particular year in terms of fire management, but also in terms of meteorological condition. In terms of meteorological condition, because we faced to some meteorological condition that favored the map up phase, which can cause each single fire to be reinitiated several times. So the dynamics of wildfires, it's quite complex. You have an ignition, so the fire spread, firefighting can go and extinguish the fires, but normally they have to stay and to be sure that the fires it's completely extinguished, because vegetation can burn in the behind, and the fire can reinitiate even some hours on even the day after, especially if you have some meteorological condition like as for example, very dry condition. That it was exactly what happened in summer 2017. Maybe it happened also before in other years, but what was special, typical in 2017, it was a change in fire management. The Italian forestry crop change that was in charge in the previous 20, 30 years for fire management was dismissed in 2016. To compare this, Liguria, as other region in Italy, named the Italian firefighters in charge of fire management. But their way of acting to extinguish fires was quite different than the usual way to do from the Italian forestry crops. The Italian forestry crops, at my knowledge, stay in the area to be sure that the fires were 100% extinguished. While in the new management, they acted with the Canadair to extinguish the fire. The Canadair fly away, and maybe the fires, because of this special unusual meteorological condition, could be reinitiated. So these results reflect that random forest could not take into account the management and meteorological condition issue for these particular years. Even if, however, it successfully predicted the area to be burned in the future, but only if the environmental and management conditions are the same, will not change. As byproduct, random forests produce also a plot with the ranking, estimate with the mean, with the error. In this plot can be useful to assess the order of to order or each variables based on their importance in predicting the fire occurrence. And this was done in winter and in summer. I don't describe this in more details because we are still working on this, since in the original data set we have some classes that were classified as Barnet area, because this we use the land use map, and it was quite we had to reclassify this in order to be sure of our assessment. So we are still working, but just nice to know that a byproduct of random forest is the assessment of the importance, is this importance ranking. In conclusion, random forest successfully produced a susceptibility map of wildfire and was able to estimate the variable importance. In Liguria, this was done in the two seasons, in summer and in winter. And more generally, this approach provides to be particularly effective to deal with the large and high-dimensional data. In this case, we used also the information from the neighboring vegetation, and so finally we had about 50 variables. That is a quite high-dimensional space. And so we can almost speak about big data in this special case. But we have to be careful in using this method, and in especially in general conclusion about your result, because as in this case, in general, machine learning can give wrong results if the model is trained on biased data, or if the condition will change in space or in time. So even if you have the best model, you have to be sure to have also the best data, and this is the most difficult things. To have a very good data set, it's really, really difficult. And so this is all for me, and this is the website of my group, and I let you, maybe I will give you also the slide to Giovanni to make this available for you. And okay, this is all for me. If you have any question, I'm happy to answer to you.
Well, thank you very much. So is there any question? So if anyone has any question, please write on the chat or unmute yourself and ask. Okay, so it seems that the presentation was clear.
So I don't know if I was looking in the chat. I don't know if you have, again, if you have already worked with machine learning, it was the case or not for them?
If in the course they are working with machine learning, you mean?